Hello and welcome to Monday's lecture for week 12, talking about light. We ended the previous chapter making the connection between electric and magnetic fields and light by talking about the Poynting vector S. We said S is equal to the cross product of the electric and magnetic fields, and that intensity of light, which how we perceive light, is equal to the average of this value, and turns out to be e squared over 2 mu naught c, or since the speed of light c is equal to e over b, we also had b squared c over 2 mu naught. In any case, the takeaway is that intensity is related to the square of the magnitude of the electric field or the square of the magnitude of the magnetic field. And when I say that we're going to talk about light for the next 2 or 3 weeks, light is just one manifestation of this electromagnetic radiation. It's really, electromagnetic radiation results from moving a charge. And if you wiggle a charge 1,000 times a second, or if you wiggle it 10 to the 22nd times a second, it still radiates. And the way we categorize that electromagnetic spectrum is like this. We have kilometer-long wavelengths that are your AM radio. And remember that the wavelength and frequency of light are related by this formula, C equals wavelength times frequency. So for all of these forms of electromagnetic radiation, they all travel at the speed of light c. And so these are just basically inversely proportional to one another. And at citizens band or FM frequencies, you have meter-long wavelengths, and at the frequency of your microwave or your cell phone, the wavelength is about 1 centimeter. And then a micron is about 1/10 of the width of a human hair, so this is the wavelength of visible light. And then X-rays, which are used to probe interatomic distances, are on the order of a picometer. And gamma rays, these are produced by nuclear reactions, including the reactions that happen in the sun, and very damaging to human tissue. So one tiny little part of this is blown up in this picture, and this represents the visible spectrum. We call it visible just because we can see in that frequency. And there's some couple really interesting things about it. One is that if you look at this picture, it looks like the center is right around yellow, which is, if you were to look at an intensity distribution of light from the sun, if this vertical axis is intensity and this is frequency, it's centered right around yellow. So yellow is the center of intensity for the sun. And your book says, oh, the center of sensitivity of our eyes is close to the same frequency as the center of wavelength distribution from that. Is that a coincidence? Well, not really, right? Because we evolved on a planet in this solar system, so it makes sense that our eyes would be adjusted, centered more or less on this frequency. But it's even more interesting if you look a little bit more deeply, and a quick Google search will reveal this for you. Our eyes are not most sensitive to yellow light. Our eyes are actually most sensitive to blue-green light, so right around here. And this is a picture from my electricity and magnetism textbook, Jackson. It's got absorptivity of light in water, so this is, to be emphasized, right? I can't draw on it, but it's in water, not in air. And it sort of behaves kind of as you'd expect, that the absorption goes down with frequency, because frequency is related to energy, and so it's going to lose more and more of that energy the higher the frequency. But something spectacular happens right at the blue-green wavelength. It just drops down like it almost goes to zero, right? I mean, the absorption is minuscule at this very narrow frequency of a very narrow range of frequencies, which happens to correspond to the range of frequencies that we can see. So our eyes didn't just evolve because, we happen to be close to the sun. They evolved to see best underwater, where this is the frequency that's least absorbed by water. And I know you probably know lots about this subject already, but I just took a little picture sort of suggesting some genetic research that shows that we may have evolved from aquatic creatures. I think that's the consensus of the scientific community at this point. And this is just one of the clues that might be the case. So then here I asked the question, how do you make a self-propagating electromagnetic field? I think I already gave away the answer. You just wiggle a charge. And one way to do that is you just put an AC generator and then you attach a wire to one end. And now charges are free to move up and down this wire. And if you make this wire correspond to a half wavelength, think back to what we were doing with mechanical waves and the conditions for a standing wave to exist on a string. And you remember that the minimum, the first mode that we could create on a string was the mode where the string was half the length of the wavelength, half of a wavelength. So this is how big your antenna should be. If you really want to transmit a maximum intensity, then make your antenna equal to half a wavelength that you're trying to transmit. So now you know if you're stuck on a stranded island, you need to transmit at 50 megahertz with citizens band frequency. You know how to make an antenna that's that big. Let's look at that. If we know C equals wavelength times frequency, and I want a half wavelength antenna, let's see how long our antenna would have to be to transmit at 50 megahertz. I get lambda equals, remember the speed of light is 3 times 10 to the 8th meters per second. And just a refresher, this came from when Maxwell was driving the wave equation. He found that the velocity term was this. And E naught is 8.854 times 10 to the minus 12th. This is 4 pi times 10 to the minus 7th. You multiply those two together, you square them, and you invert them, and you get 3 times 10 to the 8th. Okay, so over, where were we? Lambda equals C over F, and so this is 50 times 10 to the 6th, which is 3/5 of 100, so 60 meters. It's a really long antenna, which means you might want to make a quarter wavelength antenna. The reason I bring up how do you make an electromagnetic wave is that if we wiggle this charge, say up and down in the y direction on this wire, then the electric field has to be in that direction. Why is that? Because I know that F is equal to Q times E, and I know that the force is equal to mass times acceleration. Sorry, this is hard to read. That means that acceleration, this acceleration vector, and the electric field vector are in the same direction. So we define the direction of polarization of a propagating electromagnetic wave as the direction that the electric field vector points. So do you remember when we were talking about the pointing vector, and if we said we had electric field pointing up and magnetic field pointing out, then you use the right-hand rule to show that the pointing vector was going in the x direction in this case. This is y, z, x. So here's that same picture, but now looking down the axis of the gun, so S is pointing at us, and the electric field vector is pointing up. Let's say it's in the y direction, in the y-hat direction. So this is called this is the direction of polarization. That's the direction that the electric field is going in. So how do you turn something that you consider just an incandescent light source or light from the sun, any atomic source is going to be wiggling in some arbitrary direction. In fact, all of the directions, statistically speaking, are going to be represented. So that means that normal light, normal unpolarized light, has electric field vectors pointing in every direction. How do you get it to turn into light that's only polarized in one direction? Well, you probably know already because you've been probably wearing polarized sunglasses all your life. You pass it through a polarizer, and kind of one metaphor for a polarizer is a picket fence. Imagine that you try to wiggle a rope through a picket fence. You're going to be able to transmit that wave if your rope is if you're trying to wiggle the rope in the direction of the slats, and you won't be able to transmit the wave if you're perpendicular to the slats. And in some ways, it's a really unfortunate metaphor or analogy, because the way a polarizing filter really works is you align the picket fence directions in the perpendicular to the direction that you want to polarize it. So Land found this in the 50s or late 40s. He took some polymer chains, so some carbon fibers that had some free electrons that were free to move in this direction, up and down in this direction. That means an electric field that comes in the y direction would be able to dissipate its energy by moving charges up and down these carbon chains. Well, that means that all of the electric field in the direction of these carbon fibers, in other words, in the direction of the picket fence slats, would be absorbed, and only the perpendicular, only the components that were perpendicular to these picket fence lines would be transmitted. So that's how a polarizer actually works. It's kind of opposite or perpendicular to a picket fence. So we've talked about this, the geometric interpretation of dot product a bunch of times, but I think maybe this would be a good time to bring it up again. If I want to know how much of this E naught vector is in the y hat direction, how much of E naught is along y, I would take the E vector and I would dot it with y hat. And I remember, since the magnitude of y hat is just 1, this gives me E, the magnitude of E, times the cosine of the angle, between the polarizing filters and the direction of polarization of our electric field. So we're really close to coming up with just about the only formula that you're going to need to do the homework today, and that's Malus's law. And we remember from our discussion last week of how intensity is related to electric field or magnetic field. This would also, I think I wrote this earlier, but I don't know, it's not even that important. The only thing to remember, the only reason to write this down is to remember that the intensity is related to the square of the electric field or the square of the magnetic field. And so it tells us that the intensity of light that goes through a polarizer is equal to the intensity of light that goes in the unpolarized light, times the squared cosine of this angle. So this is one thing to remember. The other thing to remember is in a situation like this, where all of our polarization problems are going to be like this. You have a polarizer that takes your unpolarized light and will transmit only light that's only polarized in one direction. So this is a vertically polarized light. It's only transmitting light in the y direction. And then you have a second polarizing filter. It's called an analyzer, but don't forget, it's also just a polarizer. It's not any different physically than the polarizer. It's just called an analyzer because its polarization angle is tilted with respect to the polarizer's polarization angle. And then that allows us to mitigate the amount of light that's in the direction that we don't want. For example, reflected light off water is going to be horizontally polarized. If you want to minimize the glare from water, then you would take polarized sunglasses that only lets vertically polarized light through. So, oh, right, okay, and then there's this this relationship. The intensity of polarized light is 1/2 of the intensity of the unpolarized light. And the reason for this is because since we said that all of the directions for unpolarized light are represented, if you take the average over theta of a cosine squared function, you get 1/2. So that's just carrying out this integration. I remember we did it graphically a couple weeks ago. So know that if you take unpolarized light through some polarizing sunglasses, for example, a polarizing filter, you knock that intensity in half. And then we have to use Malus's law for this one. And let me finish this. This is IP cosine squared theta. So if you just remember the fact that the polarized light is half of the unpolarized light intensity, and the intensity coming out of the analyzer is just IP times cosine squared theta. You can solve all of the problems in this chapter. Well, for this homework anyway. So this is just a picture showing what happens when you cross two polarizing filters. If they're in the same direction, the light comes through just at half of the unpolarized light intensity. But the more you make the analyzer perpendicular to the polarizer, the more of that light is going to be blocked out, until you completely block out the incident light by making the analyzer perpendicular to the polarizer. And why is that? Because IA equals IP cosine squared theta, and when cosine is 90 degrees, that's 0. So you have 0 intensity that's transmitted. So I wanted to just do one example before we close for today, and that's, let's do a couple examples. So imagine that I have unpolarized light, and it has some intensity I0, and it goes through a polarizing filter. And that polarizer is its axis at 0 degrees. When it comes out of the polarizer, we'll say that's IP. Now, the situation I just described was, now I've got an analyzer that's at 90 degrees with respect to the polarizing transmission axis, and we said that's equal to 0. But I want to imagine what happens now if let's actually put that over here. And we'll call this IA2. Now I'm going to stick another filter in between these two, and you might expect that it's going to only make the situation worse, right? Because already we have two cross polarizers, and we showed that the intensity of the light coming out of the the analyzer is 0 because it's perpendicular to this vector. But if we stick in another one that's maybe at 45 degrees, let's see what happens now. Sometimes you're given I naught, and sometimes you just said it's equal to some intensity of magnitude I naught. So here we already know IP equals I naught over 2. Now IA1 is IP times cosine squared of the difference, and this is the key point, in the difference in the angle of the analyzer to the angle of the polarizer. Here the difference is 45 degrees because the polarizer was at 0, and this polarizing filter, it's called the analyzer, is at 45 degrees, so 45 minus 0 is 45. And the cosine of 45 is the square root of 2 over 2, and so when I square that, I get 1/2. So this is just IP over 2. Now, let's look at IA2. Before it was 0, remember? Before we put this filter in the middle. Now what is it? Well, now I've got IA1 times cosine squared. This is the mistake you might be tempted to make, is to say this is cosine squared of 90 degrees, which we know is 0, but that's not true. You've got to take the difference between these two filters. This one's at 90, this one's at 45, so I take 90 minus 45, I get cosine of 45 squared, which is 1/2 again. So this is IA1 over 2. So now if I want just back substitute for IA2, I know it's IA1 over 2, but that's IA1 is IP2 over 2. IP over 2. So this is 1/4. Okay, it's not as bright as the incoming light, but it's definitely a lot better than 0. Let's just do one more. So I have unpolarized light coming in, my polarizers at 0, my first analyzer's at 30 degrees, and my second analyzer's at 60. And what the heck, let's do a third analyzer at 90 degrees. So IA1, I naught over 2. When it comes out of, sorry, I drew it in the wrong place. I think what I need is some lines here. Okay, this is actually IP. This is IA1. I'm just going to do the substitution right away. I know that IP is I naught over 2. So now I have cosine squared of 30 degrees. Cosine of 30 is the square root of 3 over 2, so when I square that, I get 3/4. Now, IA2 is IA1, which is, let's see, 1/2 times 3/4 is 3/8. Times the cosine of, should I put 60 degrees in here? No, I have to take the difference between this polarizing filter and this polarizing filter, which is 30 degrees. And I get the same thing as before, so now 3/4 of 3/8 is 9/32. And then finally, IA3, which is 9/32 I naught times the cosine squared of 30 degrees again. I think that's about as hard as these polarization questions get. But if you have any questions, please don't hesitate to call or text.